It's actually not a secondary thought in the lecture slides. But for me, it's typically a secondary thought. And if we go through and look at kind of one of the largest crises that we have to deal with is energy and how we get energy and how we manipulate that energy and turn it into other things. So if we look at how energy is produced across timelines, you can go through and see within this graph how we're changing, how we get our energy. So you can see coal made up 51% of our energy production starting before 2015, so 2000 to 2015, and that is slowly decreasing. And instead, we're seeing an increase in natural gas. Okay? And all of those are just a way to produce energy that we can exist in our everyday lives. So that's our TVs, that's our television screens, that's our PowerPoints. Okay? All of that technology requires energy, and the question is, where do we get that energy from? One of the kind of, I guess, best sources that we could potentially, depending on your definition, would be looking at renewable sources of energies. So you're looking at hydroelectric, wind, and solar. The problem with those is that we run out of power eventually. So hydroelectric works as long as there's water flowing from a high height to a low height. So that should generally stay fairly constant. If we get floods or droughts, that's going to change the water flow. That's going to change the power output we get. Okay, so that's potentially problematic. If we look a little bit more specifically at wind and solar, those ones are a little bit more obvious as far as our power output goes. When the wind stops, our power output stops. So if all of your world is based off of just the wind blowing, we've got a problem. We can only use PowerPoints. We can only use technology when we have wind. That's problematic. Same thing for solar. I would argue a little bit less extreme for solar. It only works when we have the sun. So half of our time we're losing. We don't have the sun to generate that electricity for us. Okay, so one of the things that kind of comes to the forefront is that we can produce tons of energy through solar or wind or hydroelectric. We have the potential to do that, but we can't consume it all in that exact same instant. So we want a delay mechanism in place. That delay mechanism is lovely when we talk about natural gas and coal. We just don't burn it, and we don't have to worry about it. Okay, so we have a storage mechanism built into the system. We don't have a storage mechanism built very well into solar, and that's where batteries come into play. So the idea is that we're taking that excess energy that we aren't using it and dumping it into a storage mechanism. That would be batteries. So the question becomes, how do batteries work? How can we generate that storage? How can we manipulate that storage to get the power back out? Right, and that's a lot of what electrochemistry is looking at. So to deal with that, what's really happening is reduction and oxidation. Okay, we'll look at those in a little bit more detail. They're almost always tied to each other, which is where you'll hear reference to redox reactions. We don't call them reduction and oxidation because we're lazy, and we typically don't refer to them as just reduction reactions. Right? And that's because to do a reduction, we also simultaneously need to do an oxidation. They're tied to each other. And in all those cases, all we're doing is transferring electrons, which is great, because when we think about our energy needs, what are we trying to do? Transfer electrons. Our light works because there's an electron flow coming from a source passing through our light bulbs, which is allowing the electric flow to cause light to happen. And as long as that flows back, we're good. Okay, so it's all a transfer of electrons. It can happen both with batteries, and it can also happen within the cells. If we talk about how we produce energy as humans, okay, we burn glucose. Okay, but if we instantaneously burn that glucose, we would explode. Okay, so our cells have devised mechanisms to slowly control how we combust that glucose and transfer that energy into something other than turning into a giant fireball. Okay? That's what's happening within our cells. If we look at plants, they're doing the same thing. They're trapping energy from the sun, and they're converting that through stages into a chemical energy that we can then release later on. So all of those systems require some type of energy manipulation, which is all coming back to how we transfer the electrons from one place to another to another. Okay? So this electron transfer process is where we get to oxidation and reduction. These are two important terms that you do need to know. Okay? This is one of the reasons why, and I will even record it, I need to go back and yell at least Brian as your general chemistry instructor if you had him, because he went through and told you allegedly the stupid acronym of oil rig. I used to just yell at the biologist because apparently the entire biology department supports oil rig, but now it's seeped into the chemistry department, which is freaking irritating. Okay? What is going on with this? And we'll talk about why it's irritating for the biologist in a second. Oil rig. Number one, we're talking about oil. Oil is about dead things. Why the hell would biology use an acronym that is about dead things, not living things? The whole point of biology is to study freaking living things. Pick a better acronym. Right?
I think he provided a separate acronym that was just going on the
So it's only partially his fault? The other part is your fault?
He didn't provide that.
Okay. The next part that I would be irritated with oil rig, okay, if we go through and process it, O for oxidation. That makes a lot of sense. Okay? I for is. Who the hell uses I for the acronym of is? Seriously? That is just stupid.
You normally don't really need that, do you?
No, it's never used. So instead it should be already like, well, we got to turn it into a word. Okay. Sometimes I get irritated. You guys have mostly missed this irritation level, for the record, because it's not my lectures. Okay. And then we move to L for loss. So oil means oxidation is loss. Loss of what? Because there's nothing else in the acronym that tells me what it's a loss of. Is it the loss of pineapples, peanuts, elephants? Okay. We have no frickin' clue what we've lost because it's not actually in the statement. And instead we wasted a letter on frickin' I. Okay. So what would be a better acronym? Leo. What is Leo? Leo is another name for a lion. And what do lions do? Lions grr. Why is this relevant? Well, L stands for loss. E, electrons. I actually know what I'm losing now. And O for oxidation. Done. There it all is. Okay? And you go through to grr. G is gain. E again. Electrons are reduction. It's like it fits together. It's this beautiful system. And it talks about cool things like lions, not like bad things like oil rigs. Ultimately, you're responsible for knowing it one way or another. Okay? And so when we go through and look at a chemical reaction, we got an example here. In the course of this chemical reaction, A has those 2 extra electrons. And we look at what transitions. As we look to the products, A no longer has those 2 electrons. So A has lost electrons. What happened to B? B didn't have any electrons. And then when we look at the product, it has electrons. So therefore, it gained electrons. So we could just talk about our reactions as the gain and loss of electrons. Right? Nobody likes talking about things as they are, and instead we invent big words to try and describe them. And that's where we get the terms oxidation and reduction. Right? There's a little bit of history behind that, because if we look at what's happening within these reactions, it is the transfer of electrons, but electrons weren't discovered until 1898. Okay? So we're talking pretty darn recent history. Okay? That's Thomson's discovery. Okay? And that only worked because we were able to invent a vacuum. Before we had a vacuum, we couldn't actually discover electrons. So that's kind of wicked. Okay? So the term oxidation was something that was much older than that. So they didn't know anything about this transfer of electrons, and yet they were still able to coin a term for this. Why? What does oxidation sound like? Say again? Oxygen. Because what is happening in an example oxidation reaction? Rust. What is rust? Yes, rust is oxidation. Where does rust come from? What makes up rust? Rust, very specifically, is referring to iron in the presence of oxygen. Sometimes a catalyst will help speed it up, like salty water, which is why our boats tend to rust. So one of the first things that we're trying to move through our bronze, iron, and all of those different ages, right, was that we had problems with oxidation. That oxidation weakened the individual metals. Okay? Why did we call it oxidation? Because we were able to track that it was tied to the presence of oxygen. So if we increase the bonds to oxygen, we would call that an oxidation. And if we decrease the bonds to oxygen, that would be like we reduced the number of bonds, we would have reduction. That's where those terms are coming from. Right? Once we understand what's actually chemically happening dealing with our electrons, we now add that layer of information back to our reactions. Okay? And if we consider what's going on with oxygen, oxygen is the primary culprit when we talk about oxidation and reduction reactions. But there are lots of redox reactions that involve things other than oxygen. Why is oxygen our primary culprit? That was a deep inhale. Because there's a lot of freaking oxygen in the world. Okay? And it happens to match a chemical reactivity that allows it to run a lot of these reactions. Oxygen is a great mediator for those individual chemical reactions. We can start it in its elemental state, and we can change and manipulate it into individual compounds. Okay? That's one of our focal reasons for oxygen. Okay? So, if we're talking about these oxidation or redox reactions where we're gaining and losing electrons, we have to be able to track whether we have gained or lost electrons. Okay? Which then means we would go through and look at something known as oxidation numbers, or as I was already stating, though I don't think I actually recorded it, oxidation states. Okay? The oxidation number or state refers very specifically to an individual element or atoms, not element, an individual atom's balance of protons and electrons. Okay? Which should sound familiar. That should sound temptingly like charge. They're technically different things, and we'll deal with that a little bit later. So if we're going through and looking at these systems, our oxidation is a loss of electrons. So our oxidation number will increase. So we're going to start to become more positive. And if we look at reduction being a gain of electrons, we're going to start to see our oxidation number decrease. Okay? But we still have to know how to determine that oxidation number. Okay? So there are a couple different methods to go through and deal with oxidation numbers. And what we're looking at here as a summary of a rule is one that I would argue is more relevant for organic chemistry than it is for general chemistry, but it is still exceptionally valuable. So again, what we're concerned about is the balance of electrons for an individual atom. If I look at an individual atom, let's pick oxygen, because oxygen is cool, oxygen -2. Okay? How many protons does oxygen -2 have? How do we know it has 8? Because that's the atomic number for oxygen. How many electrons does it have? How do you know it has 10? It's +2, it says -2. How do you know it has 10?
It's the opposite of chemistry.
And there's two negative charges, which are
The upper right-hand corner is our charge, our balance of protons and electrons for that individual thing. If we go through and look at oxygen, oxygen, when it starts neutral, would have 8 protons and 8 electrons. If we make it a -2, it has to have more electrons. Since electrons are negatively charged, that's why it's a negative sign. Okay, so this isn't an issue of it being opposites, it's that we just have more of the negative thing present. That's it. Okay? So if I wanted to determine the oxidation state for this individual thing, right, it's going to be a -2. But isn't that the same thing as the charge? Sort of. The oxidation state applies to the individual atom, period, full stop. The charge applies to whatever the thing is. What is the thing that we are studying that I've drawn in? The oxygen atom. The thing and the atom are now simultaneously one unit. There is no way to differentiate them. They are the same. So in certain circumstances, your oxidation state will be the same as the charge. When is it different? What is the charge on methanol? Okay. The charge is always given to you. It's supplied in the upper right-hand corner of your formula. And when we look at the upper right-hand corner for our methanol, we see nothing written. That is because the charge is 0. If I now want to determine the oxidation state must apply to the individual atoms that make up that thing. So I've got carbons, I've technically got 4 hydrogens, and I have oxygen. I have to deal with determining the oxidation state for every single one of those individual things. Okay? How do I go through and determine that? That's going to come down to different sets of rules depending on what you're looking at. If we're looking at a structure, what we move to is this formula that we're evaluating at the top. So our oxidation number will be the number of valence electrons minus the number of electrons that each atom has. Okay? Has is a little bit weird to me. I would prefer the word owned. Or ohms in the molecule. So how do we go through and apply that? We'll pick an atom. OH is not an atom. OH would be 2 atoms. That would be O and H. I want an atom. So we've got a suggestion now for carbon. So if I'm going to look at carbon, how many valence electrons does carbon have?
In the structure or on its own?
So, and this becomes an interesting dilemma. We're saying, well, are you talking about the structure? Are we talking about its charge? No. We're talking about the valence electrons that carbon has. Full stop, period. 4. Carbon has 4 valence electrons. How do we determine the valence electrons? Ooh, I got a stick. A couple ways of doing it. You could just count the columns in the individual row. So if we look at carbon, it's in the second row. 1, 2, 3, 4. That means 4 valence electrons. How else could you do it? Did you do it that way? Okay, how else could you do it? Anybody know what IV stands for? What's that? Yeah, the Roman numerals. What does it translate to? 4. What is 14 minus 10? 4. Pretty sure that wasn't a hard question. 14 minus 10 is 4. Now you're like, well, why'd you minus 10? How many elements do we have in the D block? 10. That's why I minus 10. So carbon has 4 valence electrons. How many valence electrons does germanium have? 4. Why does it have 4? We exclude the d orbitals, which is why we could subtract that. So when we exclude the d orbitals for germanium, it's 1, 2, exclude 3, 4. That was a fun thing to do. Probably wasn't. Right? So we could count out. Or we could have just gone to the top and said, what's the Roman numeral? 4. Right? So for everybody that was turning around, let's go to the other side of the classroom and make everybody else train next the other direction. That's an interesting option. How many valence electrons does iodine have? 7. Why? Roman numeral 7. The valence electrons come from the periodic table. This should not be a new concept, right? Some people are saying, no, if you forgot, that's okay. You need to remember because it's important to calculate our oxidation states. Right? So we don't care what that atom is connected to. The valence electrons will always be the valence electrons. Period.
This might be a dumb question, but what are the D blocks? How many valence electrons do they have?
So the D blocks start to fall out of the system because they start to introduce D electrons, and those D electrons end up doing weird, goofy things. Right? So we will not worry about those. for the sake of this class because we don't want to deal with that chemistry. If you want to deal with that chemistry, that's cool. Become a chemical engineer, and then you'll probably be talking about d orbitals when you talk about semiconductors or anything like that. Okay? Because they do some very cool things, and we start to change the language because they respond differently. Okay? So then the next step, the number of electrons the atom has or owns. So we would now go back to that carbon and say, well, how many electrons does it own in this molecule? This becomes a very challenging question. Okay? And what we're really talking about, try and color code this, we'll make this purple. So that was 4 minus, and now we'll talk about its owning. Okay? That owning is in reference to the bonds directly around it. So the most electrons that the carbon could own would be 8. Okay? But now the question is does it own all 8? How do we determine ownership? So a lone pair, absolutely it would own, but carbon doesn't have any lone pairs. We'll cross that bridge when we talk about oxygen. Okay? What we're concerned about is where the electrons in that bond are spending their time. Are they spending it with the carbon because it owns them? Or are they spending it with the hydrogen because the hydrogen owns them? Or are they 100% equal sharing because they have the exact same electronegativity? Okay? So in this case, when we go through and look at it, do carbon and hydrogen have the same electronegativity? They're close, but they're not the same. And this is why I dislike dealing with oxidation states, or this rule for oxidation states. Okay? They are different. Carbon is more electronegative by ever so slightly, which means what is it doing to those electrons? It holds them. It owns them. So if we're now looking at the total, carbon, looking at this bottom hydrogen, owns those 2 electrons. Let's take a look at the hydrogen to the left. Is the hydrogen to the left any different than the hydrogen to the bottom? Nope, which means carbon owns them. How about to the top? Also owns. How about to the right? Oxygen's going to own those electrons because oxygen is more electronegative than the carbon, which means I'm going to draw those with the oxygen. So how many electrons does the carbon own? It only owns 6. So if I'm going to determine my oxidation state for my carbon, it's going to be 4 minus 6, and its oxidation state is -2.
Electronegativity increases like up and to the right?
Okay, which becomes an important thing. We have to know our electronegativity trends to be able to manipulate this. Fluorine is our most electronegative. We don't care about any of our halogens because more or less they don't react. So fluorine's our most electronegative. When you look at most periodic tables, you'll see cesium is the least electronegative. And you typically don't see francium upwards, and you typically also don't see your lanthanides and actinides. Why not? What was electronegativity a measure of? Hold on to what electrons? It's not valence electrons. Bonding electrons, very specifically. So why do we not see francium in our lanthanides and actinides? Those atoms or elements are so unstable that how many different chemical reactions have we been able to test so that we can evaluate where it's sharing or not sharing the electrons? Next to nothing. And since we don't have that data, we can't evaluate their electronegativities. Okay? So that's why they tend to disappear from the table or from our electronegativities. Right? So we've got now our oxidation state for our carbon. Does that mean we're done? No, if we're being asked for oxidation state, we need to apply it to every single atom. Right? So what's the next atom you want to look at? Cool. Let's take a look at the oxygen. Started to color the oxygen in purple, so we'll stick with it. Okay. Our oxygen's in purple. How many valence electrons does the oxygen bring in? It brings in 6. When does it bring in 6? Always. That's what it does. Okay? And now we want to see how much it owns in the individual molecules. So we look at each of the individual bonds around it and say, did it own those electrons? We already evaluated with the carbon, so we're done with that. How about to the hydrogen? Oxygen is more electronegative than hydrogen, which means oxygen is going to own those electrons. So I now go through and count how many electrons does the oxygen own? 8. Oxygen will have an oxidation state of -2. When you go through a few examples, what you're going to find is that there's patterns that start to build, particularly around oxygen and hydrogen. Okay? We'll leave you to discover those patterns because we're going to do a few more examples in a second. Okay? Once we've done those examples, we'll talk about why those patterns are coming about. We could then go through and look at the hydrogens. How many different hydrogens do we have? Okay? So we can come up with a couple different options. We can say 4, but argue it's 2. The hydrogen connected to the oxygen is definitely different than the hydrogen connected to the carbon. But how about the next hydrogen connected to the carbon? Is it any different than the first one? No. Then how about the last one? No. So I would argue there's really only 2 types of hydrogens here. Okay? That phrasing becomes useful if you say move into organic chemistry. If you don't, who cares? How many valence electrons does hydrogen have? 1. How many valence electrons does the green hydrogen have? 1. It's always the same. Okay? Minus the number of electrons it owns. How many electrons does each of those hydrogens own? 0. Which then means the oxidation state for the hydrogen comes in to be
1.
Okay? And saying 1 is fine, and looking through the slides also will navigate and just show that number. Okay? Just like in the past unit when we talked about exo and endothermics and positives and negatives, I like to specify the charge or that positive or negative sign to add extra emphasis for my sake in being able to interpret these things. Okay? So I would highly encourage you to go through and do so. Yes, sir?
So if we have like different oxygens bonded to different atoms and structure, do you need to like subscript them?
So if you have oxygen bonded to different places, do you have to subscript them? Why?
Is there like influence differently?
Okay? So what you were talking about is changing the question. I would argue we can answer your question without changing the question. We have hydrogens, right? Should I go through and subscript those as this is hydrogen 1 and that one's hydrogen 2? Okay? Yeah, we could go through and do that. Okay? And that's perfectly acceptable and allowed to go through and do that. You do have to be careful with your subscripts, though, because if I drop in an H with a 2 there, what does that start to look like? H2 hydrogen, not the second type of hydrogen. Okay? So that is a potential thing that could appear. Right? This class, I don't think it does. I'm a little nervous about making that statement, right? Because it's bit me before. But I don't think we'll have to worry about that. Okay? Questions about that? Hi. So, one of the things that we do need to be able to know is our periodic table trend. This is technically a blue box, but you already told me the answer. Fluorine was our most electronegative. And our upper right-hand corner, this was our most. We ignore our halogens, and then cesium would be our least. So really all you're trying to do is say where your elements are relative to those 2 points to decide most or least electronegative. If it's most electronegative or more electronegative, it's all relative because you're only looking at an individual bond. You're comparing the 2 atoms and saying, well, one is more electronegative than the other, therefore it owns the electrons in that bond. Okay?
This, I'm going to phrase this pretty badly, but moving this way is less than moving down, right?
So you do get subtle differences in how that works. And ultimately, the trends aren't perfect either. There are weird cases where it kind of oscillates and shuffles around. And a lot of that has to do with ultimately how electronegativity is measured. And it's a pretty half-assed measure, right? So there's a variety of different tables. You can look up tables of electronegativities, and what you'll find is a couple things. Number one, there's weird patterns where it's not following the exact trend. Okay, so something's a little bit off. Okay, the other thing that you can find is that the numbers aren't always the same. So when we look up fluorine, I want to say it's typically through, I don't remember, 4. Let's just stick with 4. Right? But you could look up another table, or I see, I'll come back to you. You could look up another table and you could see it coming at 3.5. Why are we getting different numbers? Because it's how it's being calculated. Right? It's how we've decided to evaluate what that electronegativity is. Right? And we don't have a perfect uniform example. Right? So depending on how we want to monitor it or calculate it, we'll come up with slightly different numerical values. Ultimately, as long as you're using the same consistent table, you should be fine. Because what we're doing is comparisons. If it's more electronegative, it's going to own the electrons. So you don't need to stress about the absolute value of the number, you just need to be concerned about the magnitude, which is why the trend becomes more important. Right? A little historically, this, I believe, was first coined by Linus Pauling, and he went through and did it by looking at an average of the electron affinity, so back to 151, the ability for an atom to suck an electron in. Isn't that what electronegativity is? Well, no, electronegativity was to suck an electron from a bond. Electron affinity is to suck an electron from the vacuum. Okay? So it's a different measurement. And he compared that to, or averaged that, with the ability for the atom to give up an electron to the vacuum. And so that when you combine those two pieces of information, you approximate something known as electronegativity. Right? And that's where it initially started, and we've since refined it and changed it a little bit, and ultimately really all we care about now is what those trends are. Does that kind of make sense?
Do you follow the same Ohming rules for like double plots?
Which is, I think, you started to ask something that made me think you would look at that. If we looked at the oxidation state for our carbon in this molecule, okay? So you asked double bonds, and I took it to the next level and made it a triple bond. Okay? How does that change our conversation? It doesn't. Each of those lines represents a pair of electrons, period. Okay? And if the oxygen is more electronegative, what does it do to those electrons? It owns them. Okay? It's not going to be easy to go through and draw the dots in this case, but what's going to happen is oxygen is going to take all 6 of those electrons. Which means when I go through and look at carbon, carbon has 4 valence electrons, minus how many electrons does it own? 2, and we get a +2. What do we get for the oxygen? Oxygen came in with 6 valence electrons, minus how many electrons does it own? 8, we get a -2. Okay? So multiple bonds are treated the exact same way. You just have to acknowledge that every line is a pair of electrons, is 2 electrons. That's what Lewis structure should have hammered into your head, so that if you have to navigate into OChem, you understand that better. Does that make sense? Okay. We just solved another structure for new oxidation states. What was the oxidation state for carbon in the last slide? -2. What is it here? +2. Ooh, which means the oxidation state for our carbon changes. What was the oxidation state for the oxygen on the last slide? -2, and here it is. The oxygen, -2. Interesting, it didn't change. Okay? So by running enough examples, maybe we'll start to pick up some patterns behind what's going on with our oxidation states and some kind of secondary quote-unquote rules that we could go through and apply. Okay? So, lucky us, we got a bunch more practice. These are now all in those structures, so we can match that structure system. We don't have to worry about the formula system that we'll talk about in a little bit. So, swing away. In theory, everybody was able to nail those ones down fairly well. Do we have any questions about the ones that are shown? Okay. The one that I actually got a couple of questions on and that I actually prodded people on was looking at the O2 in the middle. Okay? And that one does become a little bit trickier, but again, if we follow the rule sets, it helps us out. The oxidation state for the oxygen, so valence electrons, is 6, minus the number of electrons it owns. If we go through, for sure, if we look at just the left oxygen, it for sure owns those 4 electrons. But now we run into a dilemma when we talk about the electrons in between. How many electrons are in between? There are 4 electrons. Right? To decide where those 4 electrons go, we would have to evaluate the electronegativities. But if one is oxygen and the other one is oxygen, they're equally sharing those electrons. So how can I divvy up those 4 electrons so that they are equally shared between both oxygens?
Each one gets 2 each.
They each get 2. And if they each get 2, the oxygen on the left has those 4 dots plus 2 electrons from the bonds in between, which means I get 6 minus 6, and I get an oxidation state of 0. Okay? If we go through and look at our oxygen, okay, because now we've done a couple different examples, what do you note is fairly common for our oxygen? It sure seems to be that it is always a negative 2. We've encountered an exception right away. Okay? So let's go back to our quote-unquote rule. Oxygen is always negative 2. Why would oxygen always be a negative 2? You should be able to do a little bit better than that, but that's pretty target. The 3 most electronegative elements are fluorine, oxygen, nitrogen, in that order, which should become pretty important because when we think about our intermolecular forces that theoretically happened in 151, we have a particular strong intermolecular force that's super important, that biology loves to call a bond, that we technically call a bond that's not a bond. What's that bond? Hydrogen bonding. And hydrogen bonding works as a strong bond because we're attaching hydrogen of low electronegativity to the 3 most electronegative elements. That generates a strong dipole. That's why that molecule has a strong interaction with other things. We're trying to neutralize that charge. Okay? The same thing goes back to now looking at our structures. Oxygen being the 2nd most electronegative element, doesn't really matter what we bond it to. It is always going to be more electronegative than whatever it's bonding to, which means when we go through and run the count, it's always going to steal the electrons, and it will always be a negative 2. And of course, as soon as we say always, we have to realize there's exceptions to that. When does oxygen not steal electrons? When it's bonded to itself, because it can't steal electrons from an atom of the same electronegativity. So in that particular case, oxygen will not have a negative 2 oxidation state. Okay? It'll come in at 0. There's one more exception. When you bond oxygen to fluorine, it's also going to change its oxidation state. Why? Fluorine has a higher electronegativity, which means in that bond, fluorine's going to take the electrons away from the oxygen. That's going to change the oxygen's oxidation state. Okay? So when we think through these systems, okay, we got to be careful memorizing a rule and recognize that it's not a rule, it's based off of electronegativities, and all you're memorizing is the most common pattern that comes out of it. You have to recognize where that pattern is coming from so that you don't miscalculate later on. Make sense? Okay. Come on. Which then sets us up for some potential guidelines. Okay? The first guideline, I would argue, is the most critical and probably the absolutely most relevant. Okay? The oxidation numbers must add up to be the overall charge for the molecule. Shown a different way, if I take the oxidation state of molecule A and I add that, atom A, and I add that, suspicious empty white space, to the oxidation state of element B, this must add together to equal the overall charge. And since the overall charge is always given to me, that helps simplify my analysis. Kind of make sense? This formula does have something missing within it. Okay? It's the oxidation numbers for every single atom. If you have multiple of that atom appear, you would then have to, multiply by the number of times that atom appeared. Or you individually add them all up. Okay? The reason you would have to individually add them all up for every single atom would be because they had different oxidation states. Okay? For this class, the majority of the time, your oxidation state is going to be constant for an individual element within a compound. Okay? The only way you'd be able to see that difference is if we moved into structures. Have we looked at some structures? Yeah. Which means, could you potentially see a quiz question that shows a more advanced structure and asks you to calculate oxidation states? Yes, where you could get different oxidation states for the different elements, or for the same element. Does that make sense?
Would we have to know, like, for certain electronegativities, like, for the quiz?
All you need to know is the trends.
Gotcha.
So to give you an idea of a potential example where you could get in trouble by not accounting for or not going by individual atoms, this particular compound is going to generate a carbon or two carbons with different oxidation states. Okay? So we would have to account for them independent. Given the structure, we have to assume they're independent and we would have to calculate it. But if we were instead given the formula, we don't know anything about the connectivity within that formula, and we have to assume they're all the same. Does that make sense? Okay, so be aware of those different systems on what you're going through, and I put too many hydrogens on that oxygen. I knew something was bugging me. Okay, so you'd have to be aware of those potential systems to kind of watch out for those issues. Sir? But you don't know how to convert a formula into a structure. Okay? So there's nothing for you to draw out because you literally lack the skills to be able to do so. Okay? And since you lack the skills, we can't expect you to go through and do that. Not with a structure this complex.
So on an exam, would we have the picture or would we have the formula?
I don't know.
Because how
So-
would we find the oxidation number?
So we're going to encounter a couple issues here. So we could say for that formula, we have two carbons times its oxidation state. Do you know the oxidation state of carbon? Silence is sort of okay. No, we don't. So that's X. Plus, how many times did hydrogen show up? 6 times its oxidation state. We'll start that with an unknown for a Y for the moment. Plus, how many times did oxygen show up? 1. We'll go with Z. Okay, and then this has to equal 0 because there's nothing written in the upper right-hand corner. Okay, so to answer your question, how could you solve for that? X, Y, and Z. That's 3 variables, one equation. You can't possibly solve for it, except what is Z? Z must be a -2. What is Y? Y is going to be a +1. Why is it going to be a +1? Because hydrogen has the lowest electronegativity within this set, which means by definition it's going to give up its electrons, which means it's going to come in at a +6, and I'm going to get 2x + 6 - 2 equals 0. Can I solve for x? That's how you do it. Does that make sense? So there are bits and pieces that you have to be able to process and kind of intuit through with those potential unknowns. Oxygen being the primary one. Okay? The rest of these rules are, I would argue, a bit silly. Neutral elements by themselves will always have an oxidation number of 0. Okay? So let's erase all that work down there. Let's pick the default example, sodium metal. What's its charge? 0. There's nothing written in the upper right-hand corner. So I have 1 sodium times its oxidation state equals the overall charge of 0. What is the oxidation state? 0. I don't have to memorize a rule if I understand the first premise.
There's no bonds, so it would just be the valence.
Okay? And there's no bonds to worry about, so I don't even have to worry about that either. The other option, we could make it more complex and we could look at Cl2. Well, what's its overall charge? 0. How many chlorines are there? Well, there's 2. What's its oxidation state? I don't know. 2x equals 0. What's x? X is 0. I would argue that middle rule is utterly useless if you understand the premise of how we're doing this. Okay? The last one, monatomic ions, the oxidation numbers equals the charge. Okay? This one's going to hit a little bit different because I would argue, again, Mg plus 2. It's going to be a bit silly because we go through and do that one. How many magnesiums are there? 1 times its oxidation state, I don't know what it is, has to equal the overall charge. What's the overall charge? Plus 2. So the oxidation state is plus 2. Okay? Again, I don't need a rule for that if I've paid attention to the number one premise behind this. But there is a little bit of undercurrent on this one that we've got to watch out for. That undercurrent would be this. How do we do that one? We can't do 2x because the magnesium and the bromine are different elements. So if we're going to follow our formula, we'd have 1x plus 1 bromine, y equals an overall charge of 0. We have x and y, those are unknown variables. How do we go through and solve? Okay. We sort of have a structure here. Admittedly, I've got charge balances being problematic. So we could go through and evaluate the individual structure, or what kind of bond is that in red? Someone said it. It's an ionic bond, see? Ionic, ionic, see? It's funnier when I explain it. Okay? It's an ionic bond, and if it's an ionic bond, what does that mean I can do? I can split it into the ions. What's the ionic form for magnesium? Mg plus 2. What's the ionic form for bromide? Br minus. This isn't now one expression. I can solve it 2 ways, or with 2 expressions. I have 1 magnesium times an unknown oxidation state equals positive 2. Oxidation state is positive 2. I can go through and look at the bromide. Times an unknown oxidation state must equal the overall charge. What's the overall charge? Negative 1. What's the oxidation state for the bromide? Negative 1. Okay? So that third rule has this kind of hidden implication behind our ionic compounds, which is why it's important to know our charge balances of our ionic compounds, which is why you studied nomenclature back in 151. Not so that you knew the names, but that you understood the charge balances behind how you put those things together. Because now what we can do is take them apart to help solve our oxidation states. Kind of, sort of? And I said I was going to get back to it, and yep. Yeah, okay, almost. Okay. This slide is in there, and it actually technically shows up twice. Initially, it had a different periodic table that I felt didn't really show the oxidation numbers. What I believe this is attempting to go through and show is that there are certain patterns that we could potentially follow, and really what we're trying to highlight here is the ionic charges. So the ionic charges are things that you should have learned in Gen Chem. Ideally, in my opinion, you should have memorized to simplify your flow when dealing with future chemistry questions. Okay? And when we go through and look at those common ionic charges, when we're looking at an ionic compound, how do we know we have an ionic compound? Metal and a nonmetal. Cool, we memorized that, right? We can now use that to separate it into the individual ions, and as long as we knew the common ion charges, we could then determine the oxidation states. Okay? The problem I've got with this is this suggests a trend. The trend is really only applicable to the ionic charges, not to the oxidation states. And the ionic charges are following what trend? What's the ionic charge for fluoride? Okay, cool. We should talk about that trend. Okay. Fluoride doesn't have a full valence, right? So it's unhappy. To look happy, what does it need to look like it has a full valence? Neon, because neon has a full valence. So what does fluoride try to do? Gain an electron. And so the common ionic charge for fluoride will be -1, so that it can look like neon. How about chloride? -1 also, so that it can look like, it doesn't look like neon though. It looks like argon, the noble gas closest to it. And if we went through and looked at sulfur, what does sulfur try to do? It's going to try and look like the noble gas. Okay, the closest noble gas to it, which would be argon. The easiest way to do that would be to change the number of electrons, -2. So fluoride, -1. Oxygen, -2. Nitrogen, -3. Carbon. Why did you say plus or minus?
That's what they told me. Tutoring said.
Okay. So what they told you was this plus or -4 is technically wrong. It's +4 through -4. Go back and look at the oxidation states that we determined for our carbon. It was not always a -4 or a +4. We had lots of +2s. We had a minus, I think we just had a +2. And the other one, we had a -2 in there too. Okay? So carbon hits the smattering across the board. So it has all of those possible charge states. Okay, so let's go back to the +-4. Why are they saying +-4? What is carbon trying to look like? A noble gas. So it could gain 4 electrons. 6 + 4 would be 10. So and if it gains 4 electrons, its charge would be -4, because it has an extra 4 electrons, and the electrons are all negative. Or it could have looked like neon. That's not neon. Helium, thank you. Okay. How does carbon look like helium? I lose 4 electrons. And if I lose things, clearly it becomes negative. Why does it become positive?
You're losing a negative charge.
The electrons were negatively charged. That's why we're hitting the spread of +4 and -4. Why did we not see that for nitrogen? Couldn't nitrogen also become positive? It's going to look at the ease of what it's trying to do. Nitrogen can gain 3 electrons to look like neon, or it could lose 5. What's an easier trade? Okay, gaining those 3. So when we look at the ionic charges, or the common ionic charges, that's what we're evaluating. You're comparing it back to the noble gases. I believe that is the trend that we're trying to highlight within this. And you can go through and match those. What you'll end up finding is that when we look at the transition elements, all hell hits the fan and everything becomes a big mess. Okay? And that's because the transition elements bring in a whole nother layer of junk with the d orbitals. Okay? And again, if you like d orbitals, they are really cool. They do some phenomenally fun and interesting things. That would either be a chemical engineer interested in semiconductors, or that would be an inorganic chemist, which you would learn if you moved into an advanced inorganic chemistry class. Kind of, sort of. Which then sets us up with, ta-da, assign your oxidation numbers. So we'll go back to this. You now have a better rule set to be able to go through and build and determine the oxidation states. I want the oxidation states for each of these elements. Okay? For the record, as walking around, maybe I didn't see your work, just to be clear, but when I walked around, I did not see anybody who had actually assigned the oxidation numbers correctly. Okay? I'm not trying to be mean. I'm just making sure you're aware that you should go through and check and make sure you're doing it right. So we've got all the oxidation states and how I would go through and do it. Technically, I didn't do the sodium chloride, mainly because I said that one was too easy. Okay? But if we split the sodium chloride, because it's an ionic compound, we get sodium plus and Cl minus. So you're going to get sodium has an oxidation state of +1. The chloride has an oxidation state of -1. We go through and look at the aluminum hydroxide. Again, ionic compound. I've got that metal. I can go ahead and split that into the individual ions. I've got Al+3 and hydroxide. Note the 3 as that subscript I've dropped off. That's telling me I have 3 hydroxides to balance the aluminum. When I'm splitting it into the ions, I don't care how many are there. I just care how many of that atom in that unit is there. The unit is hydroxide, so I don't need to stress about it. If you want to bring in the 3, you can. That just changes your mathematics a little bit, okay? And it's just universally going to get applied all the way through, which will ultimately mean it just falls out of the expression. Okay? So if we got aluminum with our hydroxide, the aluminum straightforward, oxidation of +3. Officially, the hydroxide, I should have done a formula system like I did with the black one at the bottom, okay? But I jumped to oxygen being a -2, which means the hydrogen would have to be a +1, so that I got an overall charge of a -1. Kind of, sort of? Yes?
So the main assumptions we can make are oxygen and hydrogens?
The main assumptions are going to be oxygens and hydrogens, yes. Oxygen will be a -2. Hydrogen will usually be a +1. There are more exceptions with hydrogen being negative than there are with oxygen changing its oxidation state, because hydrogen can be bonded to metals. As soon as hydrogen's bonded to a metal, it's got a higher electronegativity and the whole system flips. Right? If we go through with the next one, we can split it into the ions. We've got iron +3 and oxygen -2. We would know those charges because of our nomenclature balancing practice that we did back in 151. So that simplifies that split because I go straight to the oxidation states. If I didn't know that, I would then go through and do the same kind of formula system that we worked out for the last one. We go to the last one again, ionic. I can split into the ions, lithium ion and then the nitrate. The lithium ion is straightforward. The nitrate becomes trickier. I have 1 nitrogen plus 3 oxygens. The oxidation state of oxygen is a -2. That's going to be equal to -1. That gives us the oxidation state of nitrogen coming in at a +5. Okay? All too commonly, students will go through and say the nitrogen is a -3. Okay? If we said the nitrogen was a -3, does our formula check out? -3 minus 6 does not equal -1. Okay, so ultimately that means what you did was you tried to memorize the ionic charge. The ionic charge only works when you're looking at an ionic bond. Between nitrogen and oxygen, that ain't ionic. That's a covalent bond. You have to change the dynamic of that system.
Can the oxidation state be not whole number? Like Fe, like you can't do that. It'd be 2x equals 3, right?
What? No. So I see what you're trying to do. What you were trying to go through and do is say that we had 2 irons here. So if we switch that, it would be 2 times x equals +6. Why would it be +6? Because I have 2 of those +3s. This is the exact multiplier thing that I would say you would drop out. So that 2 as a multiplier, if you just ignore it and say, what's the ion? The ion is Fe+3. I may have 2 of them, but the ion is Fe+3. That simplifies my analysis. So to your question of can you end up with fractional oxidation states, mathematically you'll encounter situations where it could come in as a fraction. And ultimately what that means is that you have that element show up multiple times within whatever unit you're looking at, and they have different oxidation states. That's how you're getting a fractional one. Okay? So the formula is going to force you into a fractional oxidation state. But officially, no, because it's a balance of protons and electrons. Okay? With that, we are done.